Now, dear students, let's discuss exercise of chapter number 5. Okay. Now, example 5.1. The sign of work done by a force on a body is important to understand. State carefully if the following quantities are positive or negative. First, A. Work done by a man in lifting a bucket out of a well by means of rope tied to the bucket. So here the work done will be positive because the man applying the force on the bucket in upward direction like this. He is pulling the bucket. Okay, and bucket is moving in upward direction. So as per W equal to FD cos theta, theta that is 0. So cos 0, 1. So work done that is positive. Okay. Now, question B. Work done by gravitational force in above case. Now bucket is moving in upward direction and gravitational force that is in downward direction. So both are in opposite direction. So in this particular case, the work done that will be negative because cos 180 that will be minus 1. So W that is equal to minus FD. Then work done by friction on a body sliding down an inclined plane. The frictional force that is always in the opposite direction of motion. Therefore, in this case also, the work done that will be negative. Clear? Now, work done by an applied force on a body moving on a rough horizontal plane with uniform velocity. So, to move the body with uniform velocity, when we apply external force, then the force that will be in the direction of motion. So again here cos theta that is cos 0 that is 1. So W that is FD and that is positive. Clear? Then next one. Work done by the resistive force of air on a vibrating pendulum in bringing it to rest. When resistive force bringing this pendulum in rest, it implies that it is opposing the motion. So resistive force that is in the opposite direction of the motion. So again in this case, the work done that will be negative. Clear to all of you? Now example 5.2. A body of mass 2 kg initially at rest moves under the action of an applied horizontal force of 7 Newton on a table with coefficient of kinetic friction 0.1. Compute the A. Work done by the applied force in 10 seconds. B. Work done by friction in 10 seconds. C. Work done by the net force on the body in 10 seconds. D. Change in kinetic energy of the body in 10 seconds. And interpret your result. Okay. Now see here. Mass of the body is given to you. Initially it is at rest, means initial velocity that is 0. Then applied horizontal force that is 7 Newton. Now here we want to compute work done in these different cases in 10 seconds. So under the effect of this net force, what is the displacement of the body that we have to first find out, because work done that is force into displacement. So in 10 seconds, what is the displacement that we have to find? Now here friction is also there. So what is the frictional force, applied force that is given to you, and what is the net force? All this we have to calculate. Then after we have to calculate acceleration, because using that we can calculate the displacement. Okay. So force of friction, that is Fk, it is kinetic friction, so mu k into R. R that is normal reaction, so that is mg. So mu k into mg, mu k that is given to you 0.1. m that is 2, g that we can take 10. So the answer is 2 Newton. Now 7 Newton force is applied, friction is 2 Newton. That is in the opposite direction of the applied. So here net force with which the body moves, that is F dash equal to F minus Fk, 7 minus 2, that is equal to 5 Newton. Clear? Okay. Now the acceleration, that is the net force upon mass. So net force, that is 5 Newton upon mass 2, so acceleration, that is 2.5 meter per second square. Here net force is constant 1. So acceleration is constant 1. So we can use the equation of motion with constant acceleration. So we have the equation S equal to ut plus half at square. Okay. So distance covered in 10 seconds, that is S equal to ut plus half at square, u that is 0, half a 2.5, t 10, square of it. So distance covered, that is 125 meters. Now see here, first we want to calculate work done by the applied force. Applied force is 7 Newton. Clear? And displacement in 10 seconds, that is 125. So work done by the applied force W1, that is F into S, 7 into 125, that is 875 joule. Second, work done by friction. So again frictional force into displacement. So work done frictional force into displacement, but frictional force that is in the opposite direction of displacement or in opposite direction of motion. So here we have to introduce negative sign. So minus Fk into S, that is minus 2 into 125, that is minus 250 joule. Third one, work done by the net force on the body in 10 seconds. So net force into displacement. So work done by the net force W3, that is F dash into S, F dash 5, S 125, so that is 625 joule. Change in kinetic energy. Change in kinetic energy, that is whatever is the final kinetic energy, because initial, that is 0. Because initially the body is at rest. So change in kinetic energy, that we can write by calculating final velocity after 10 seconds. So V equal to U plus AT, U0, A 2.5, T10, so 25. Now change in kinetic energy, that is half m V square minus half m U square, but half m U square will be 0 because U that is 0, half m that is 2, V square that is 25 square, so again it is 625 joule. So here see, work done by net force, that is equal to change in kinetic energy. So this one is as per work energy theorem. Clear? Now example 5.3. Given in figure are example of some potential energy functions in one dimension. The total energy of the particle is indicated by a cross on the coordinate axis. In each case, specify the regions, if any, in which the particle cannot be found for the given energy. Also indicate the minimum total energy the particle must have in each case. Think of simple physical context for which these potential energy shapes are relevant. Okay. So here potential energy versus position graphs are given to you, and on graph the value of total energy that is given by cross and the potential energy that is given by V0. Okay. Now see here, we know this thing, total energy, that is kinetic energy plus potential energy. Okay. So kinetic energy, that is E minus potential energy. Now kinetic energy, that is always positive. Okay. So the region given in the graph for which the kinetic energy is positive, in that the probability of the particle is there. If the region in which kinetic energy is negative, then particle can't be exist in that particular region. Now, this one is the fundamental thing. Now, let's analyze each graph. Now, see here, in this particular graph, here, the potential energy after x greater than A, that is greater than total energy. It implies that here we can see this thing, the kinetic energy that is negative in this particular region. Okay, so here the particle cannot exist in this particular region where x is greater than A, and here E minimum, that is 0. Clear? Next one. So here see, V0 starting from x equal to 0 to onwards, in each region the potential energy that is greater than total energy. So kinetic energy is negative in all the regions. Clear? It implies that the particle cannot be found in any of this particular region, right? And here E minimum, that is minus V1. Okay, then after third one, so see here, in this particular region E, that is less than potential energy, and in this region also it is less than potential energy. So here we can see this thing, x less than A means in this particular region. Okay, and x greater than B means in this region. Okay, kinetic energy will be negative, so particle cannot be found in this particular region, right? And E minimum, that should be equal to minus V1. Actually, see here, there is a printing mistake in this graph also. On this side, like this, there is minus V1. Keep this thing in your mind. Okay. Then fourth one. Now, see here. So, in this one also, you can see in this region, okay, and here in this particular region, okay, the potential energy that is greater than total energy, and after this one, okay, the potential energy that decreases than total energy. So from minus b by 2 to minus a by 2, as well as from a by 2 to b by 2, the kinetic energy will be negative. So particle cannot be present in this particular region. And again here E minimum, that should be equal to minus V1. Clear to all of you? Now example 5.4. The potential energy function for a particle executing linear simple harmonic motion is given by V as a function of x, that is half kx square, where k is the force constant of the oscillator. For k equal to 0.5 Newton per meter, the graph of Vx versus x is shown in the figure. Show that a particle of total energy 1 joule moving under this potential must turn back when it reaches x equal to plus or minus 2 meter. Now see here, the total energy that is given to you 1 joule, k force constant, that is 0.5 Newton per meter. Now when oscillator is oscillating like this, at that time the total energy that is constant and that is equal to kinetic energy plus potential energy. Whenever the oscillator reaches at the extreme position, then momentarily it becomes stationary. Its velocity becomes zero. So kinetic energy becomes zero. So entire total energy that is converted into potential energy. Clear? So at the extreme position, total energy and potential energy will be equal and kinetic energy will be zero, right? And extreme position, that is the position from where it comes back. Okay? So here total energy, that is E equal to K plus V. So E equal to half mv square plus half kx square. At extreme position, its velocity, that is zero, and particle turns back. And at extreme position, when you substitute here V equal to 0, then E equal to half kx square. Okay? So E, that is 1 half k 0.5 into x square. Clear? So x square, that is 4. So x equal to plus or minus 2. So here we can say this thing, the position plus or minus 2 meter, it comes back. Clear to all of you? Now example 5.5. Answer the following. A. The casing of a rocket in flight burns up due to friction. At whose expense is the heat energy required for burning obtained? The rocket or the atmosphere? So it is obtained due to rocket itself or by rocket itself. Okay, so burning of casing of the rocket in flight is obtained from the rocket itself, right? It is obtained at the expense of the mass of the rocket and its kinetic and potential energy. Okay. Then B. Comets move around the sun is highly elliptical orbit. The gravitational force on the comet due to the sun is not normal to the comet's velocity in general. Yet the work done by the gravitational force over every complete orbit of the comet is zero. Why? Because we already discussed this thing, the gravitational force, that is the conservative force. And for conservative force, the work done on the closed path, that is always zero. Clear? Then see, an artificial satellite orbiting the earth in very thin atmosphere loses its energy gradually due to dissipation against atmospheric resistance, however small. Why then does its speed increases progressively as it comes closer and closer to the earth? Because when it comes closer and closer to the earth, its potential energy decreases. And when we neglect this atmospheric resistance, here it is given to you, however it is small, then we can say the total energy is almost constant. So when potential energy decreases, kinetic energy increases, and therefore its velocity increases or speed increases. Okay. D. In figure 1, the man walks 2 meters carrying a mass of 15 kg on his hands. In figure 2, he walks the same distance pulling the rope. Behind him, the rope goes over a pulley and a mass of 15 kg hangs at its other end. In which case is the work done greater? Now see here, in this first case, the weight, that is mg, and displacement, that is in horizontal direction. So force and displacement are mutually perpendicular. So in first case, the work done, that will be equal to 0. Clear? But now if we think about Second case. Then see here, man is applying the force on this particular object by this rope. So here the pulling force, that is in this particular upward direction, and displacement, that is also in upward direction. So here if man walks 2 meter, then displacement of this body, that will be 2 meter in upward direction, and a pulling force by rope, that is also in upward direction, right? And this work is done against the gravitation, that is in downward direction, mg. So here work done, that is mgh. So 15 into 9.8 into 2, so that is 294 joule. Here you can take 10 also, so you can write 300 joule. So in second case, the work done, that is greater than the case in 1. Clear? Now next example 5.6, underline the correct alternative. A. When a conservative force does positive work on the body, the potential energy of the body increases, decreases, remains unaltered. So as per theory, we discussed, we can say potential energy here decreases because kinetic energy increases in positive work. B. Work done by a body against friction always result in a loss of its kinetic or potential energy. So frictional force always opposes the motion. So loss of kinetic energy will take place in this particular case. C. The rate of change of total momentum of a many particle system is proportional to the external force or sum of the internal forces on the system. So obviously it proportional to the external force. Sorry. D. In an inelastic collision of two bodies, the quantities which do not change after the collision are the total kinetic energy or total linear momentum or total energy of the system of two bodies. So in theory we discuss this thing, in any type of collision, total linear momentum and total energy remains constant. But only in elastic collision, sorry, kinetic energy remains constant. So your answer will be total linear momentum and total energy. Clear? Now example 5.7. State if each of the following statements is true or false. Give reason for your answer. Now see, A. In an elastic collision of two bodies, the momentum and energy of each body is conserved. False. Here, the momentum and energy of each body is not conserved, but the total linear momentum and total energy of the entire system that conserves here, not of individual bodies. B. Total energy of a system is always conserved no matter what internal and external forces on the body are present. False, right? When external forces are there, then in some cases external force may change its energy. Okay? Then C. Work done in the motion of a body over a closed loop is zero for every force in the nature. No, it is not necessary. The statement is false because the work done is zero over a closed loop only in case of conservative force, and in nature it is not necessary all the forces are conservative forces. Then D. In an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. Yes, true. In theory, we already derived the equation for the change in kinetic energy for inelastic collision, and we can say this thing here always the final kinetic energy is less than initial, because during the collision some energy is lost. Clear to all of you? Now example 5.8. Answer carefully with reasons. A. In an elastic collision of two billiard balls, is the total kinetic energy conserved during the short time of collision of the balls? It implies when they are in contact. So here, when the collision takes place at that time, momentarily means for a short time interval, kinetic energy is converted into potential energy. So during the contact, kinetic energy is not conserved, but before the collision and after the collision, the kinetic energy remains same one. Clear? Then B. Is the total linear momentum conserved during the short time of an elastic collision of two balls? In any type of situation, always the total linear momentum that conserves, right? C. What are the answers to A and B for an inelastic collision? So if the collision is inelastic, then also the answer A and B, that will remain the same one, there will be no change. Okay. D. If the potential energy of two billiard balls depends only on the separation distance between their centers, is the collision elastic or inelastic? Not, we are talking here of potential energy corresponding to the force during collision, not gravitational potential energy. So here in this particular case, the forces involved are the conservative forces, and therefore the collision that will be elastic collision. Clear to all of you? Now exercise 5.9. A body is initially at rest. It undergoes one-dimensional motion with constant acceleration. The power delivered to it at time t is proportional to what? So we have one equation for the power, that is power equal to force into velocity, right? So at any time t, what is the velocity of the particle which one is moving with constant acceleration? So first that we can find with the equation v equal to v0 plus at, but initially it is at rest, so v equal to at. Now power p, that is equal to force into velocity. Force F, that is ma into v, but v, that is at. So we can write ma square t. Now mass of the object, that is constant one. Acceleration, that is constant, is given to you in the question. So we can say, now in this case, power directly proportional to time t. So as per given options, our answer that will be second one. Clear? Now exercise 5.10. A body is moving unidirectionally under the influence of a source of constant power. Its displacement in time t is proportional to what? Option 1, t raised to 1 by 2. Option 2, t. Option 3, t raised to 3 by 2. Option 4, t square. Right? So here the power, that is constant one, that is given to you. Now with the help of power, if we find out the equation of velocity, then we know this thing, velocity, that is ds by dt, differentiation of displacement with respect to time t. It implies that if we integrate velocity with respect to time t, then we will get displacement. Clear? So here first we take power, that is w upon t. So w, work done, that is power into time, right? And work done w, that is change in kinetic energy. So change in kinetic energy, that is final kinetic energy half mv square. So W, that is P into T, that is half mv square. Now we want to find V first. So we can write V square, that is 2 pt by m. So V, that is 2 pt by m raised to 1 by 2. Now 2 is constant, P is constant, m is constant. Clear? Now here we can write V, that is a function of T only. So V, that is ds by dt. So that is 2 pt by m raised to 1 by 2. If we integrate this particular equation, then S equal to integration V dt, integration V, that is 2 pt by m raised to 1 by 2 dt. 2p by m raised to 1 by 2, take it outside the integration because it is constant one, and then integrate t raised to 1 by 2. So power will be increased by 1 and then will be divided by power. So t raised to 1 by 2 plus 1, whole thing divided by 1 by 2 plus 1. So we can write 2p by m raised to 1 by 2 into t raised to 3 by 2 upon 3 by 2. So here 2p by m raised to 1 by 2 and this 3 by 2, that is constant part. So we can say the displacement proportional to t raised to 3 by 2. It implies that as per given option, here option number 3, that is the correct choice. Now exercise 5.11. A body constrained to move along the z-axis of a coordinate system is subject to a constant force F given by F equal to I caret minus I caret plus 2j caret plus 3k caret Newton, where I caret, j caret, k caret are unit vectors along the x, y and z axis of the system respectively. What is the work done by this force in moving the body a distance of 4 meter along the z axis? Now see here, force given to you, that is minus I caret plus 2j caret plus 3k caret Newton. Now here the body is moving by a distance of 4 meter along z axis. So in this case our displacement vector, that is 4k caret meter. Now we want to calculate work done. In theory we studied this thing, work done W, that is F dot S, dot product of force and displacement. So W, that is F dot S, that is minus I caret plus 2j caret plus 3k caret dot 4k caret. Now simplify this one. So we can write now minus I caret plus 2j caret plus 3k caret dot 0 I caret plus 0 j caret plus 4k caret, this one. Now here simply if you write down this one like this, then minus 1 into 0 I dot I, then 2 into 0 j dot j, then 3 into 4 k dot k, but this k dot k, that is 1, j dot j 1, but this one is multiplied with 0, this one is also multiplied with 0, so cancel. So our answer, that is 12 joule. Clear? Now exercise 5.12. An electron and a proton are detected in a cosmic ray experiment. The first with kinetic energy 10 keV and the second with 100 keV. Which is faster, the electron or the proton? Obtain the ratio of their speeds. Electron mass, that is 9.11 into 10 raised to minus 31 kilogram. Proton mass, that is 1.67 into 10 raised to minus 27 kilogram. 1 electron volt, that is 1.6 into 10 raised to minus 19 joule. Now see here, kinetic energy of both the particles, that is given to you. Okay, and mass is also given to you. So if you want to find which one is the faster one, then we have to calculate the ratio of their speeds. So take the ratio of kinetic energy of electron and proton. Kinetic energy of electron, that is given to you 10 keV, and that is half mv square, mass of electron, speed of electron. Kinetic energy of proton, half mpvp square, that is 100 keV. Take ratio of these two. So kinetic energy of electron upon kinetic energy of proton, that is half MeVe square upon half mpvp square. Now this ratio 10 keV upon 100 keV equal to 1 by 10. Half will be cancelled. Now substitute the value of mass of electron, 9.11 into 10 raised to minus 31 into Ve square upon 1.67 into 10 raised to minus 27 into Vp square, and that is 1 by 10. Now solve this one. You will get Ve square upon Vp square, that is equal to 183.3. Take square root on both the side. So you will get Ve upon Vp, that is 13.53. It implies that when this ratio is greater than 1, then we can say numerator is greater than denominator. It implies that speed of electron is more than the speed of proton. So electron moves faster than the proton. Clear? Now exercise 5.13. A raindrop of radius 2 mm falls from a height of 500 meter above the ground. It falls with decreasing acceleration due to viscous resistance of the air until at half its original height. It attains its maximum, means terminal speed, and moves with uniform speed thereafter. What is the work done by the gravitational force on the drop in the first and second half of its journey? What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meter per second? Now see here the given information. Radius of the drop, that is 2 mm, that is 2 into 10 raised to minus 3 meter. It is falling from the height of 500 meter. And its final speed, that is 10 meter per second. Now first we want to calculate the work done by the gravitational force during first and second half. First and second half, the distance covered, that is same one. Gravitational force in both the half, that is same one. So during both half, the gravitational force will do same work. Okay. So work done by gravitational force during each half, that is Wg equal to mg into h by 2. M, that is mass of drop. That is not given to you. That we have to find. Okay. So mass, that is volume into density. Volume, that is 4 by 3 pi r cube. Density is rho. Now substitute the values. 4 by 3 pi r, that is 2 into 10 raised to minus 3 whole cube, and density, that is 10 raised to 3. So our answer will be 32 pi by 3 into 10 raised to minus 6 kilogram. Substitute this value here. So am 32 pi by 3 into 10 raised to minus 6, g 9.8 into h by 2. Okay. So work done by gravitational force on the raindrop, that is 0.082 joule. Clear? Now second part. What is the work done by the resistive force during the entire journey? Right? Now see, for the entire journey, the total work done, that is work done by gravitational force during the entire journey. So for each half, we calculated the work done by gravitational force. And we can write that is 2 times Wg, that is the total work done by gravitational force during the entire journey. Right? Plus, during the entire journey, there is the work done against the resistive force. So that is Wr. And net work done, that is equal to change in kinetic energy. It's free falling, so initial velocity, that is 0. So whatever is the final velocity related to that, the final kinetic energy, that is half mv square. That is the change in kinetic energy. Now we want to calculate this WR. Okay, so make WR as a subject of equation. So half mv square minus 2wg. So WR, that is half m, that is 32 pi into 10 raised to minus 6 by 3. V square, that is 10 square minus 2. Wg, that is 0.082 that we calculated previously. Now solve this one. We will get the answer minus 0.1623 joule. Here the work is done against the resistive force. Therefore, automatically it appears here negative. Clear to all of you? Now exercise 5.14. A molecule in a gas container hits a horizontal wall with a speed 200 meter per second and angle 30 degree with the normal and rebound with the same speed. Is momentum conserved in the collision? Is the collision elastic or inelastic? We know this thing. During any type of collision, the total linear momentum always conserves. So we can write momentum is always conserved whether the collision is elastic or inelastic. Now say during the collision, initial speed and final speed both are same one. Speeds are not changing. Therefore, initial and final kinetic energies are also same one. So we can say when kinetic energy is also conserved, the collision is elastic collision. Clear to all of you? Now exercise 5.15. A pump on the ground floor of a building can pump up water to fill a tank of volume 30 meter cube in 15 minutes. If the tank is 40 meter above the ground and the efficiency of the pump is 30%, how much electrical power is consumed by the pump? So here electrical power is delivered to the pump. That electrical power is converted into mechanical power, and at the cost of it, here the work is done to lift up the water up to certain height. Now when the tank is full, we can say the volume of the water, that is equal to volume of the tank, that is V equal to 30 meter cube. It is lifted up to 40 meter in time interval 15 minutes, so 15 into 60, 900 seconds. Clear? So here the mechanical power obtained or mechanical power consumed, that is output power, that is work done upon time. Work done, that is mgh upon time t, mass, that is volume into density into gh upon t. So if we substitute the value, volume, that is 30 meter cube, density 10 raised to 3, g 10, h 40 and t 15 into 60. You will get the output power, that is 40 into 10 raised to 3 by 3 watt. Now efficiency, that is given to you. Efficiency, that is output power upon input power into 100, so that is in percentage. So here we can write now input power that we want to calculate, that is electrical power which we supplied. So input power, that is electrical power consumed, that is output power upon efficiency into 100. Now output power, that is 40 into 10 raised to 3 by 3 into 30 into 100. So it comes to 44.4 into 10 raised to 3 watt. Clear to all of you? Now exercise 5.16. Two identical ball bearings in contact with each other and resting on a frictionless table are hit head-on by another ball bearing of the same mass moving initially with a speed v. See this figure. 2 and 3 are in contact, are stationary, and 1 is moving with speed v and collide with 2 and 3. If the collision is elastic, which of the following figure is a possible result after collision? So here it is given to you the collision that is elastic one. So in elastic collision we know this thing, after collision and before collision the kinetic energy that remains same. It implies that during elastic collision the kinetic energy conserves. So here we have to check out of these three figures for which collision the kinetic energy is conserved. Now see, in first case means before collision, right? The total kinetic energy of the system, that is half mv square, because 2 and 3 are stationary. Now after collision, if we think about the case number 1, then in case number 1, first one, that is with velocity 0, and 2 and 3 are moving with velocity v by 2, that is given to you. So the kinetic energy after collision, that is the kinetic energy of 2 and 3 combined, because 1 is stationary, so its kinetic energy is 0. So kinetic energy, that is half, 2 and 3 are joined together, so total mass is 2m, both are moving with common velocity v by 2, so v by 2 square. So it comes to 1 by 4 mv square. Now 1 by 4 mv square is not equal to half mv square. So first case is not representing the possible collision. Second case. Now after collision 1 and 2 become stationary and third one is moving with speed v. So after collision we can calculate the kinetic energy, that is half mv square only of third one, 1 and 2 are stationary. So here we can observe this thing in case number 2, the kinetic energy is conserved. So this case number 2 is the possible result after collision. Let's check for third one. Now after collision, here it is shown 1, 2, 3 combines move with common velocity v by 3. So in third case, the kinetic energy, that is half into 3m into v by 3 whole square, and that comes to 1 by 6 mv square. So in this case also kinetic energy is not conserved. So we can say finally case 2 is the only possible result of the collision. Clear to all of you? Now exercise 5.17. The bob A of a pendulum released from 30 degree to the vertical hits another bob B of the same mass at rest on a table as shown in the figure. How high does the bob A rise after the collision? Neglect the size of the bobs and assume the collision to be elastic. Now in the theory of elastic collision, we studied about the special cases. And in special cases, we discussed this thing when two spheres are with same mass. Then after collision, first will move with the velocity of second one and second one will move with velocity of first one. Now here, when A collide with B, so B is a stationary. So after collision, A will take the velocity of B, that is 0. So A will be stationary. And B will move with velocity of A. It implies that after collision, B will move with velocity of A and A becomes stationary at the position of B. So when A becomes stationary, then here the question is how high does the bob A rise? So bob A will not rise to any height. Clear to all of you? Now exercise 5.18. The bob of a pendulum is released from a horizontal position. If the length of the pendulum is 1.5 meter, what is the speed with which the bob arrives at the lowermost point? Given that it dissipated 5% of its initial energy against air resistance. So let's first try to understand the situation with the help of figure. Right? See, here the pendulum, which one is with length L. So when it is placed in the perfect horizontal position, then we can say with respect to the lowermost point, it is at height h, which is equal to the length of the pendulum, and that is 1.5 meter. So when it is in the horizontal position, its total energy, that is kinetic plus potential. Kinetic energy is 0 and potential energy, that is mgh. Now when it is released from this position and when it reaches at the lowermost point, 5% of initial energy, so initial energy, that is mgh. So 5% of initial energy is lost against air resistance. It implies that when it reaches at B, its 95% energy is now converted into kinetic energy, because at the lowermost position the potential energy becomes 0. So entire potential energy will be converted into kinetic energy. But 5% loss is there. So we can say this thing, at position B, the kinetic energy half mv square, that is 95% of initial energy, and that is 95% of mgh. Clear? So here we can write half mv square, that is equal to 95 by 100 mgh. Now m will be cancelled. Now if we make v as a subject of equation, then that is equal to under root 2 into 95 into gh upon 100. Substitute the value of g and h, and then after solve it, then you will get v, that is equal to 5.3 meter per second. It implies that when your pendulum reaches at the lowermost point, then its velocity, that is 5.3 meter per second. Clear? Now exercise 5.19. A trolley of mass 300 kg carrying a sandbag of 25 kg is moving uniformly with a speed of 27 km per hour on a frictionless track. After a while, sand starts leaking out of the hole on the floor of the trolley at the rate of 0.05 kg per second. What is the speed of the trolley after the entire sandbag is empty? So here, when the system, means the trolley plus sandbag, is moving with constant speed 27 km per hour on a frictionless track, at that time no external force is acting on it. Okay? And when sand starts leaking out of the hole on the floor, so at that time also no external force is acting on it. So when no external force is acting on the system, if the system is stationary, it will remain stationary, and if it is in the motion, then it will continue the motion with uniform velocity, that we studied previously in the theory of Newton's first law of motion, right? So here we can say this entire system will continue its motion with the same speed when entire sandbag is empty. Clear to all of you? Now exercise 5.20. A body of mass 0.5 kg travels in a straight line with velocity v equal to ax raised to 3 by 2, where a, that is equal to 5 meter raised to minus 1 by 2 s raised to minus 1. What is the work done by the net force during its displacement from x equal to 0 to x equal to 2 meter? So to find out the work done by the net force during its displacement, first of all we have to calculate the net force acting on it. Force, that is mass into acceleration. So first of all we have to find acceleration. Here velocity, that is given to you. So We know this thing, acceleration, that is the rate of change of velocity. Means if we differentiate velocity with respect to time t, we will get acceleration. Now here mass is given to you, displacement, that is from x1 equal to 0 meter to x2 equal to 2 meter, and a, the constant appearing in this particular equation, that is 5 meter raised to minus 1 by 2 s raised to minus 1. Clear? Now, velocity v, that is equal to a x raised to 3 by 2. So a, that is 5. So you can write 5x raised to 3 by 2 or keep a as it is. Okay? Now, acceleration, a, that is equal to dv by dt. But see here, velocity, that is given to you as a function of displacement, not as a function of time. So directly we can differentiate it with respect to time. So we have to make an adjustment as shown in this step. We can write this is equal to dv by dx into dx by dt. Now, dv by dx, that is d by dx of ax raised to 3 by 2 into dx by dt. This dx by dt, that is nothing but velocity. And differentiate this one, a is constant, power will be in multiplication and power will be decreased by 1. So 3 by 2 ax raised to 3 by 2 minus 1, that is 1 by 2 into dx by dt, that is v. But v, that is again ax raised to 3 by 2, so substitute here. So 3 by 2 ax raised to 1 by 2 into ax raised to 3 by 2. So x raised to 1 by 2 plus 3 by 2, that is x square. So resultantly you will get acceleration, that is 3 by 2 a into a, that is a square into x square. Now the net force. Net force, that is mass into acceleration. So acceleration, that is 3 by 2 a square x square into mass m. Now see here, force is a function of x, means it is a variable force. Now work done under the effect of variable force, that we discussed. So that is W equal to integration f dx from x1 to x2. Clear? Now here substitute the values f, that is 3 by 2 m a square x square dx, limit 0 to 2, m a square constant, integrate x square. So you will get 3 by 2 m a square, integration of x square, power is increased by 1 and then divided by power. So x cube by 3 and limits 0 to 2. This 3 will be cancelled. So here m, that is 0.5, a, that is 5, square of it, substitute upper limit, then minus lower limit. And if you solve this one, you will get the answer 50 joule. It implies that here the work done by the net force during its displacement from 0 to 2 meter, that is 50 joule. Clear to all of you? Now exercise 5.21. The blades of a windmill sweep out a circle of area A. If the wind flows at a velocity v perpendicular to the circle, what is the mass of the air passing through it in time t? Second question, what is the kinetic energy of air? C. Assume that the windmill converts 25% of the wind's energy into electrical energy and that A equal to 30 meter square, V, that is 36 kilometer per hour, and the density of air is 1.2 kilogram per meter cube. What is the electrical power produced? So here the information given to you, that is area of the circle, that is 30 meter square, speed of the wind, that is 36 kilometer per hour. So multiply it by 5 by 18, so you will get 10 meter per second. Density of air, that is rho, equal to 1.2 kilogram per meter cube. Now in first question we have to calculate mass of the air passing through it in time t. So from the circle, whatever the amount of wind passes, right, that will be accommodated in a cylinder having cross-sectional area equal to A and length which is equal to the distance covered by the wind or air. Distance covered in time t, that is V into T. So we can write here the volume of the air passing through the windmill in time t, that is area of the circle into distance covered by wind in time t. Area of the circle, that is A, distance covered, that is Vt, so that is AV into T. This is the volume. Now density, that is mass upon volume, so mass, that is density into volume. So mass of the air passing through the windmill in time t, that is M equal to density into volume, so density into AVT. Clear? Now, what is the kinetic energy of air? So kinetic energy, that is half m v square. So we can write kinetic energy, that is half m v square, m, that is rho AVT. So half rho AVT into v square. So we can write half rho AV cube into T. Clear? This is the kinetic energy. Now 25% of this kinetic energy is converted into electrical energy, right? So the kinetic energy of air converted into electrical energy in time t, that is K dash equal to 25% of K. K dash, that is electrical energy. So 25 by 100 into K, that we derived previously, half rho AV cube into T. So this is equal to 1 by 8 rho AV cube into T. Now we want to calculate the electrical power. So electrical power produced, that is the electrical energy produced per unit time. So K dash by T. So we can write that is equal to 1 by 8 rho A V cube. Now substitute the values here. So 1 by 8 rho, that is 1.2, area, that is 30, and speed, that is 10, 10 cube. Solve it. You will get the answer 4.5 into 10 raised to 3 watt. So that is equal to 4.5 kilowatt. Clear to all of you? Now exercise 5.22. A person trying to lose weight dietary lifts a 10 kilogram mass 1000 times to a height of 0.5 meter each time. Assume that the potential energy lost each time she lowers the mass is dissipated. Question A. How much work does she do against the gravitational force? B. Fat supplies 3.8 into 10 raised to 7 joule of energy per kilogram, which is converted to mechanical energy with 20% efficiency rate. Then how much fat will the dieter use up? So see here, 10 kilogram mass is lifted up to height h equal to 0.5 meter for 1000 times. So first of all, we have to calculate the work done against the gravitational force. So work done against the gravitational force, that is mgh, when one time it is lifted up to height h, but here it is lifted 1000 times. So work done against the gravitational force W, that is n times mgh. Substitute the values 1000 into 10 into 9.8 into 0.5. So you will get 49,000 joule. Now here it is given to you in second question, 3.8 into 10 raised to 7 joule of energy per kilogram, which is converted to mechanical energy with a 20% efficiency rate only. So mechanical energy supplied by 1 kilogram of fat. that is 20% of 3.8 into 10 raised to 7 joule. So here 20% of this one, so 20 by 100 into 3.8 into 10 raised to 7. That comes to 76 into 10 raised to 5 joule. Now simply we can use here the unitary method. 76 into 10 raised to 5 joule of energy, right? That will be obtained by burning of 1 kilogram fat. Then fat consumed for 49,000 joule of energy is how much? So we can write 1 into 49,000 upon 76 into 10 raised to 5. So we get the answer 6.45 into 10 raised to minus 3 kilogram. Okay? Or we can write that is 6.45 gram. Clear? Now exercise 5.23. A family uses 8 kilowatt of power. A. Direct solar energy is incident on the horizontal surface at an average rate of 200 watt per square meter. If 20% of this energy can be converted to useful electrical energy, how large an area is needed to supply 8 kilowatt? B. Compare this area to that of the roof of the typical house. So here energy incident per unit area, that is given to you 200 watt. Only 20% of this one is converted into useful electrical energy. So useful electrical energy obtained per meter square, that is 20% of 200. So that is 40 watt. Okay. Now 40 watt electrical energy is obtained from 1 meter square. Then our required 8 kilowatt, that is 8,000 watt, that will be obtained from how much area? So area needed, that is 8,000 upon 40, that is 200 meter square. Now compare this area to that of the roof of a typical house. Now see here, we can use the roof of the given house only 70% for the installation of solar panels, right? So 70% of 20 meter into 15 meter, that we consider 20 meter long and 15 meter width of the roof of a typical house. Then 70% of it that we can use. So it comes to 210 meter square. Our required, that is 200 meter square. So for the comparison, we can say the required ratio, that is A by A dash. So 200 by 210, that comes to 20 raised to 21. Clear? Now the entire chapter is completed.